So please mute your microphone if you can. Today, it's a real pleasure to have Manu Prakash, our first guest speaker after the summer break. And I will take a minute or two quickly to briefly introduce him. There are so much to say, but what I want to, just to make it brief, I've been in this community since 2014. But I've only heard about Manu around 4 years ago when I was a postdoc in Hawaii, and a friend of mine in oceanography department texted me and say, "Hey, you should listen to this Zoom talk by Manu. You would love it." Indeed, I listened to his talk, and it's basically lit my brain, and it was so fascinating and exciting that I tweeted about it, something that I have never done before. Maybe that was my introduction to Twitter. Manu is an inventor, a professor in the Department of Bioengineering at Stanford University. He's a physicist by training, and much of his lab focuses on biophysics and frugal sciences. He grew up in India, and as a kid, I would like to recall this story because it's interesting that it may gives like student this like dynamic of this first moment of life that can, lit your brain or make you fall for science. So he recalled that when he was a kid, he moved to a new house, and the tenant next door couldn't pay the rent. So he was kicked out, but he was a chemistry teacher, and the landlord, instead of taking money, essentially took over his little lab in the basement in a garage. And him and his brother walked in that wonderland and spent a significant portion of their life, about 3 or 4 years, if I'm correct. Mm-hmm. And in that lab, it was the first experience for his science at home. Manu has a significant contribution in the field of biophysics and frugal sciences. I will mention just briefly a few of them, like, for example, the full foldscope that many of you know. It's an optical microscope that can be assembled from simple components, including a sheet of paper and lens. There are over 2 million users worldwide now about it. There is a fantastic website about it. It has other contributions like the gravity machine, the project website for open source ventilator. They did some work on COVID testing. They did a lot of other open source modular microscopy platform, and many other contributions in addition to the science and biophysics. More recently, I don't know if you saw that, there was a paper in Science that did the cover with one of his students who did the Elliott Flom. And they give the first example of cellular origami discovered in protists. It's a remarkably complex behavior, and all without a nervous system. So today, it's our immense pleasure to have Manu with us, and the virtual stage is yours, Manu.
That's very, very kind. Thank you so much. And I have to sort of just begin by saying, I was bummed I was not able to make it to the microscale meeting. So I know many of you spent time together in the microscale physics meeting over the years. And this particular one, I was really looking forward to. And so it just is kind of it would have been fun to do this much more in person, but I'm also delighted. I can see lots of familiar faces in the crowd too. So I'm really hoping this becomes a way for interactions and conversations. I'm going to try to keep myself on time, which is very rare for me, just so that we have plenty of time for questions and other threads. But feel free to interrupt me. There's really no agenda. Out of large number of things we could cover, I just was going to cover a few sets of things, but then we can have conversations along the way. One of the things that I often think about is this painting. This is Charlie Harper. It's a very well-known graphic artist. And, I think one of the things that really dawns on me when I think about this painting often enough is how he represented biodiversity of life. I think for many of us, we have known that microbes. So if you look at the lion right there, and you look right on top of the lion is Giardia. And I don't know whether knowingly or not, Charlie was trying to depict this idea that microbes are at the least of equal importance in many ways. And it just kind of, I think, in our normal dialogue in life, in our normal conversations in society, we think quite a lot about how do we bring the microscopic world in front of everyone. And I think this as a community itself, both for discovery of new sets of ideas, just the importance of microbial life in our daily life. I think this is always a reminder to me. And often enough, when you look at the tree of life and you ask ourselves a question of how much do we know about the biological world, and you compare that to just the breadth, astounding breadth of biodiversity, I think it's been said many times, and I just like repeating this framework, that for every set of a question or an idea that you might have that you're thinking about, there's possibly a species out there that is the optimal set of species to study that framework or that question. So I won't talk about this, but this idea of behavior in single cells, we worked for a very long time looking for a class of protists that would be ideal to be able to ask those questions and explore. This notion of going out to the tree of life as a way of an approach for mapping to the sets of questions you care about is, I think it's deeply valuable. It's really underappreciated. And I mean, some of this community definitely cares about being able to explore the tree of life as a whole. So the talk, I could actually organize it by a tree of life. We could just hop around from one portion of the tree of life to the other. And maybe at the very end, if I have time, I'll kind of mention some of these other surprises. Although I'll try to stay focused more on the marine snow work that we've been doing more recently. So, I think first of all, one important lesson to take away is, and you'll see some of this play out, but I still don't believe that we truly understand now, talking about plankton, the shape and form and the associated functions. And this is also generally true in cell biology itself. I mean, this is kind of one example of just a whole bunch of protists that we think about. And only in few rare cases can we truly connect the functionality of many of these things in an aquatic context. And again, this is really also where the physical parameters and the physics of some of these sets of things lie. But the fact that it's remained an open question for so many of them for so long is kind of surprising. Right there on top, you can actually see number 14 is Lacrimaria oler, which I was talking about in the context of origami. Okay, so I think I will just focus on one set of ideas around what we've been calling an ocean on a tabletop. But if you're just broadly interested in microscale physics, there's lots of recent stories that you can take a look at, and I'm happy in Q&A to talk about some of them. Okay, so I think, what do I mean by ocean on a tabletop? It'll kind of become clear in a second. But an important parameter or a premise that we've been thinking about for a long while is, how do we bring ecology back to cell biology? For the longest time, when we've taken the approach in thinking about cell biology and cellular sets of questions, we've stripped away the notion of an ecosystem, that many a times these organisms live in very strange and dynamic and changing ecosystems. And as experimentalists, it's become an important paradigm for us to make sure that we are able to bring those ecosystems back into the questions that we care about. So that was the premise of what we've been trying to do. We're not there as yet completely, but the dream really is to be able to build experimental systems that can emulate significant portions of what a microscale environment that a single microbe might actually be seeing or facing. And especially some of the organisms, and almost all of the data I'll show you today was actually collected at sea. So we've been taking these sets of instruments at sea and making these measurements at sea. enabling us to truly also see organisms as quickly as, from the point of view of collection to the sets of observations that we're interested in. So I think I'm assuming all of you have been at sea at least once, or is there anybody, show of hands, who has not been at sea? I'm just curious. Because this whole is not about oceanography. So if you don't, okay, I see no raise of hands, so I'm assuming, but if you have not, the ocean is a wonderful kind of an infinite space. Every time I go out, I'm just inspired and also realize how small we are. And there is a sense of challenge as well. So all the data that you're going to see is collected in conditions like this. And I think this is kind of one of the art of instrumentation that's been important for us, is to making sure that we are able to do precise experiments in open waters. And that's been an important premise for why we develop many of these things. I think I don't have to say this to this crowd particularly, but just, I think it is valuable to point out more broadly that the oceans have been acting as a remarkable sink, and we'll talk quite a lot about this. I would argue that our quantitative metrics and measures for both how that sink works and from a microphysics perspective, I know many of you are interested in working in that space. We still have a long gap to fill. And to me, this feels quite urgent, not only because we need to understand how the planet and the ocean sink works, but simultaneously understand how it might be changing. And this has become really critical in this field of marine CDR, primarily because there is lots of technologies being proposed at this point where explicitly ocean is the driver for being able to do carbon sequestration, while we still don't understand the fundamental mechanics of how things operate and work at play. So that tension has been kind of difficult to think about. And no matter whether we get to make that decision, whether some large-scale experiments will happen in our oceans or not, we have to take a measurement-based approach to this. And I know this is why, if many of you are thinking about or already work on a measurement-based approach, I think that's kind of the framework that we have taken, is we would like to build a standardized way to make measurements at sea for the biological pump. So let's kind of dive in, and I'll give you a framework for the types of questions we're interested in. But if the talk on marine snow would not be complete without these pioneering people, and not just BB that was in the bathysphere with Otis, but also Allison on the top. And kind of one of the things that's been described from these sets of first observations and the window of observation really changed our view of the ocean and the depth of the ocean. I think bathysphere is in display somewhere in New York if you want to go and see it. And there are versions of them also in Woods Hole. One of the things that I often think about is the power of observation itself, because these sets of primary observations is what led us to start thinking and building our view of this world. And then, another set of an observation, I very recently got a chance to go to the English Channel and just see the mountains of Dover. I know some of you might have seen this, but if not, try taking a trip. It really is a breathtaking example of micro-scale single cells enabling this large-scale transport that occurs to the bottom, literally building mountains. And I think to a certain extent, it's really remarkable that some of this flux actually accumulates at the bottom. So let's kind of take a view on where we are and what would we sort of like to achieve in this set of a framework. So historically, I think there has been a large amount of work in this field of carbon cycle in the ocean. And I would argue that I think there has been a remarkable set of tools that have been developed, there are debates that go back and forth whether we still have a good, clean carbon budget or not. And so I'm not going to talk too much about that debate, but I think what we have been thinking quite a lot about is still majority of the assays we have are indirect ways for measuring flux. And there's lots of fitting parameters that allow people to be able to make sense of different parts of these data sets. And what we asked ourselves was a very simple question, is could we build a way of thinking about direct measurements at sea for the microscale physics of marine snow particles? And although I will mention some of the other species and kind of other work that we do with these sets of tools, but marine snow will be at the heart. And I think I would be curious in terms of conversations of how other people are starting to realize the microscale data that we all collect, how do we actually incorporate that in some of these larger scale models? We have our own ideas, but we are just starting to begin to think about that. So I think most of you know this, but this is just really kind of a very simple picture to think about for how does POC transition into a sink. It's a gravity-driven process, and of course, it's incredibly complex. And that complexity, I don't believe, can be captured in a lab setting. I really admire a lot of experiments that have done in these simplified ecosystems, but one of the approaches that we have taken is to be thinking about directly measuring it at sea. And that has led to around 6 expeditions so far. I'll just show you data from 1 or 2 of them, but this is a much larger data set that we're starting to collect. The goal and the objective is very simple. We go out to sea, we collect these sinking particles using traditional sediment traps. We've recently been using gel traps. We've also been doing in situ some amount of imaging to corroborate the structure of these particles in situ imaging. We bring them on board and then we study them particle by particle over long periods of time while emulating the sedimentation dynamics for these particles. And that's going to really be at the heart. And what we care about knowing is how do these particles change? What does it look like from the context of the ecosystem, depending on what we see in the top layer? And very recently, we've also initiated and started degradation assays. And the way that I like to kind of tell this story, although I might not have time to tell all 3 stories, is I kind of borrow a lot of inspiration from astronomy. So if you were to think about the birth, life, and death of a star, that's kind of one of the 3 phases we often think about marine snow, which is the aggregation phase, which is birth. Life is really the true sedimentation cycle that it'll go through. And the death is the remineralization and many a times the eventual escape of this set of a particle to the bottom of the ocean. And most of the time today, we'll talk about life and maybe a hint of birth to begin with. And I want to remind, this is a question that people have been asking for the longest while. But even as early as 98, in some of Farouk's papers, when he would describe these sets, I love this sketch because the sketch is still very true to our picture, but we've just been adding a lot more details to these sets of scenarios. And to a certain extent, the Martin curve itself, I think one of the desires that we have with these sets of measurements is to really be able to build a quantitative framework to derive Martin's curve in kind of ecological settings. So Martin's curve is this exponential decay of flux going downwards that many of you have seen, probably contributed to itself as well. But I would argue that it's still, when I look at it, when I think about it, I often see many missing pieces that I cannot describe it as a law. And very recently, for a lot of kind of expeditions, we've actually seen kinks in these curves too, where a completely new biological phenomena happens, and then many of our physical models completely break down. And I think this is the biggest message that I want to share today, is unless we can include biological parameters in these sets of frameworks, we will not be able to build robust sets of models around these sets of scenarios. And I'll talk about one specific biological scenario. And, you know, I think this has been talked about quite a lot in what's happening as discussions around the IPCC and the context that the microbial world is truly not as yet captured. Microscale physics is not as yet captured in many of our global models. And, you know, microbiology needs to be at the table. Okay, so kind of let's just take a picture of the setting. We are mostly interested in the vertical stratification of life in the ocean. We do this by putting sets of probes, capturing sets of scenarios, also doing capture that are very precise in a known depth. And we'll talk quite a lot about these sets of gradients along the way. You know, I think one important lesson to just think a little bit about is, you know, all of you have thought about motility. We work on motility quite a lot. I'll try to kind of keep motility at bay today, although I absolutely love it. But I will show you this video just to give you a sense of to a certain extent, I'm not talking too much about the interactions per se, because we're still at the basis of understanding individual organisms and particles. But it's astounding when you really think about the density and the number of interactions that you might actually see. And as yet, I mean, this really is an inspiration. This is a video taken on a live night dive. And of course, possibly some of this concentration is happening because of the lights that are being used itself, but to a certain extent, there is actually abundance. And the number of interactions that we often think about, we have to be thinking about, at least in this framework. And I think the other thread that we've been asking ourselves as a really fundamental question, which more recently has been very fruitful, is what seemingly non-motile cells. We have often thought of them as passive objects that are at the mercy of the ocean, and I'll show you data today that that's really not actually true. So I think these are coccolithophores, diatoms, several dinoflagellates that we've been working on. We've been able to show completely new mechanisms for density regulation leading to vertical stratification in the ocean. Okay, so kind of let's take a moment and think a little bit about what this non-motile thread might look like. So for average cell, you know, you might talk about 5 to 10% density change from seawater. And that would make us assume that a diatom just passively sinks in the ocean. And I think that's not true. And one of the things that's been quite fascinating is to really see how do we discover and find new molecular mechanisms that enable these sets of density regulations. You know, this is a precursor to much of the stratification itself. Most of you know this very well. You can think about, I think we will mostly consider between the 0 to 100 meters and the 100 to 1,000 meter transition. We have started working on some really deep sea sinking particles, but I don't have that data here. And, you know, you can think about this in the context of the simplest perspective of a Stokes law, implying there is a density and there is a certain set of a size that could give you a sense of how a passive particle sink. And much of the data I really want to show you is to just say how wrong we can be when we take this approach and only this approach. I think it's kind of the ideas is we have to really be thinking about extensions of these ideas. Okay, so I think how do we sample? We primarily use sediment traps. Surface tethered sediment traps are the primary mechanism of all the data sets that you would see. I am excited about trying some of these more advanced trapping techniques. But for most of the data, it's been quite sufficient. Sediment traps are easy and fun to use. But one of the challenges that arises in all of these questions in kind of these ecological sets of questions is that the length scale that we are interested in the one dimension is quite long, while on the other hand, we want to be able to make microscopic measurements. And that was the tension. And just historically, this is a historic kind of an artifact of the process of invention. We were actually working on schistosomiasis with one of my graduate students, Deepak, And we were working in Madagascar at that time. And this happens to be a parasite that we have worked for many years now and continue to work that infects humans. And it travels along ponds and lakes and quite deep lakes. And we were interested in measuring how the parasite finds humans. This is just the nonlinearity of the process of thinking. And in that process, we started building these ultra tall microscopes. These microscopes are still useful if some of you are interested. You can see this is a scanning. This happens to be a 5-meter tall microscope. There is an imaging system. There is a Fresnel lens there. We can make water columns. And this is what we were doing out in Madagascar. We would catch snails and we would observe the entire water column. And in that process, it kind of occurred while packing for this trip that what if we created an instrument that was an infinite loop of water? And the simple idea was that what if we took those two ends and joined them together to really actually make a wheel? And that's what led to this technique. We call this scale-free vertical tracking microscopy. Now, this has become quite far advanced. I'll show you kind of the recent advances that we have built. But one of the goals really is that we want to create a microscope where the field of view is truly infinite. And so you can observe a single particle in its own frame of reference, sinking, swimming, going wherever it wants to go. And you can track it and keep it in your field of view. So you are traveling, but from a hydrodynamic perspective, the particle is actually sinking. That kind of was the premise. And, you know, this is the simple idea. If some of you have already read this paper is a couple years old now. This is one of the older versions. I'll actually show some of the new version of the instruments. These instruments have gotten quite sophisticated now. We can do volumetric imaging, 3D tracking. We can get all the way down to a 60x objective at this point. These sets of wheels that we build and design that you can see a little bit of it on the right are glass wheels. We have done a lot of work on these wheels at this point to be able to change the kind of salinity, temperature, provide cues. But this is at the heart of the instrumentation. And just, you know, I think there is an important parameter and a criteria for what can we actually track with a framework like this. So just to be very clear, if it was not obvious, I'll just kind of mention what are we actually doing? It's very simple. So this is some coral larva data. We do a lot of work on Acropora. And you're watching the data sets that we collect, for example, for this coral larva would be for 11 days in a microscope. So we can map the entire trajectory of development of a single larva the entire time the organism is in the water column. And you're seeing a tiny portion of that data set. So kind of behavior as a function of development. And the way we are able to enable that is with tracking the wheel is turning in the opposite direction. And just to give you kind of a sense of these were the early versions of the machines. You can see the object that's being tracked. This is Pyrocystis, one of the dinoflagellates that we study. This was the old days. This is now in a temperature-controlled space. And if you can't see this visually, but that was moving. And then kind of one of the fun things about this is all happening at sea. So most of the data that you'll see today, other than that coral data, is actually at sea. And there's a big number of people that have joined now who have contributed to the development of the tool itself. So this is a large team at this point, and we're starting to grow. Okay, so let's just see what the current instruments kind of look like, and then we'll go back to the, I have to wait for this animation. So some of the current instruments, we can now control temperature very precisely. We have had a few expeditions in the Arctic, so we've had to go down to 4 degrees C. The other aspects of the instrumentation is around volumetric frame rates. So we can do around 9 to 10 volumes simultaneously. So I'll show you kind of what that looks like. It's somewhere here. So This is a couple of optical tricks with liquid lensing. So now the gravity is pointing this way and you're watching a Pteria miniata larva. So I'll just play that one more time. And as you can see, we do this for 3D volumetric reconstruction. And one of the nice things about this is that we can go arbitrarily fast with these sets of techniques, because at this point, a lot of work has already happened in the sense of faster sensors, faster liquid lenses. I'm going to skip some of this because I'm running out of time already, but I want to show kind of this is all in the 2019 paper, but it's actually kind of an interesting paradigm to think about, making sure that we are not injecting any inertia in the system. So that allows us, given an organism, we back calculate the entire rotational flow in a system like this. And there is that red line that you see, which is a channel width and an object speed. So if there are some connoisseurs of copepods, I know Kirby I've spoken a lot to, the jump is too fast. If we were to actually track the jump of a copepod, we would have had to move the stage fast enough that would induce the kind of inertia. So that falls outside that regime. But there is a trick that we use. For objects that travel faster than this red boundary, we have a 2-camera setup that now allows us to do macroscopic tracking and microscopic tracking. And it's perfectly okay if we lose the object in the microscopic track, as long as we know where it is on the macro. So this is a dual lens system. And then we can slowly get to that place. So although you don't get the data for that fast jump, you can still, and because we are interested in copepod behavior, and we've had to use that trick many times in terms of finding sets of objects. And I think in that original paper, there's also a calculation that we show that's around the torque and what is the unstable regime of generating enough shear that we might flip. And one interesting modality that we've been using the microscope now is there is a trick with using the Z error on the microscope for, rather than tracking it to bring it to the center, by keeping that off center, we actually can also apply hydrodynamic forces that are lateral to the object. So there are hints that we can actually convert this system into a little bit like an optical trap as well, but with no optical trap, but purely hydrodynamic forces. That's kind of work in progress, but it's kind of fun to share and think about. Okay, let me transition to data because otherwise I'm going to run out of time. But let's just start with a few visual threads. So first of all, this is, I'll let you guess what that is. Any guesses what you're looking at? And now I've turned the machine on. So up till now, it was not tracking, and now it's tracking. So you're syncing in frame of reference. This is candy. This is sprinkles that our kids put on ice cream every day. And you can see suddenly there is an incredible number of interactions you can observe and watch. Now you are syncing in the frame of reference of these objects. And of course, there's tons of hydrodynamic effects right here. I'll show you one simple one. This happens to be the kiss and tumble effect. Most of you have probably seen some of the theoretical frameworks around this. But the one on the right is something that we are pursuing and is quite interesting. You're watching sugar in your cup of coffee. So I'll play that one more time. Just focus on the video playing on the right. That's essentially a single sugar cube dissolving as it's sinking. And we can track something like that for hours. And of course, the feedback loop that we are studying is sedimentation, shape change, and this as a particular object actually transitions from an inertial regime to a non-inertial regime itself as well. So there's lots of fun complications, but I know many of you care about the biological world, so this is kind of to give you a framework for what we can do. This is now that same Pteria miniata larva that I showed you. This is a 40x objective. And at this point, we can watch neural dynamics, single neurons firing in this organism as it's climbing meters. So this has kind of been a big thread for us to be able to understand how the ring nervous system in many of these organisms actually control its motility behavior. And so we've pushed the technique quite far, and it's been really delightful in some sense to first just make a behavioral map of the plankton. At this point in the data set, there is roughly around 600 species. So I could just spend hours showing you data sets from each one of them. We're releasing this entire data set as kind of an open data set of behavior. This will be the largest plankton behavior data set as far as I know. This is just to give you a context of the types of behavior we collect. We can track organisms for long periods of time, but many a times we will also just do shorter sets of tracks. We can introduce a cue. We can introduce a drug, for example. But what you're seeing on the left, and then you can see on the right, you're now in the frame of reference. And then you'll suddenly see there is a behavioral transition that happened right here. And of course, this is all played really fast. And so what we are first interested in is really mapping what do organisms actually do. And in that frame, this has also we've been running workshops in places around the world. This was the workshop in Naples, teaching and training people. And that's really expanded the data set significantly itself. And then before I start on the particular stories, I do want to mention something which has been really exciting. We haven't written this yet, but it's valuable to show it to all of you. Out of the 600 species that we have found so far, that we have done these behavioral data set, there is only one species that I have found so far that does not care about the gravity axis. And I'll let you guys guess. Anybody wants to guess what that is? Since I'm running out of time, I'll just show it to you. The video you're about to watch is a tracked video of a tintinid. These are these remarkable ciliates. So we're putting the story together now. But one of the fascinating threads around this is gravity taxes is ubiquitous in the ocean. And rarely do we actually do find organisms. So this happens to be a tintinid behavior that we're tracking in the set of an instrument. And many a times, of course, in its sedentary stage, when it pulls the cilia down, it does actually sink and reorient. But in its swimming phase, it really often, you see no correlations with the gravity axis. So kind of this is where the data set is collected from. So this is 600 species, 5 years, roughly around 17 expeditions total. Some of them are in the Arctic and Antarctic. Majority of them are at marine stations. And I think I'm very excited about this as a framework to see if we can build generalized theories of behavior of plankton. So kind of to now jump into, let's talk about a few sets of things. And again, we have been very lucky to have access to boats. So much of the data you're about to see was collected on Kilomoana, Sikoliak, and both Arctic and Antarctic. And I think maybe I'll show a little bit of data from the Arctic. But one of the fascinating things is that much of this data is from the ocean itself. Okay, so now since, some of this data is published itself in the 2019 paper, but we'll be releasing these sets of data sets in a much larger kind of an open frame soon enough. Okay, so let's just jump to a few organisms for a second, and then we'll kind of really switch to marine snow. So this is Serratium, for example. So some of you have thought about this is what I meant by role of gravity to begin with. So you can see that the object that we're tracking in this long distance has this instability. And often enough, you'll see, and of course, this is a motile organism. So there is a cilia on the top, and that shape kind of derives one of the reorientation cycles that I was talking about in gravity. This is another organism. It's quite rare. It's actually also, this is Tiarina. It's the only ciliate that I know that biomineralizes and actually has a symbiont. We were very lucky to actually find a bloom of Tiarinas in Villefranche. And it's kind of interesting. It's a ciliate that travels with an armor. And so what you're watching is this, this massive climb that it does, but it is being heavy. It's carrying this massive ballast of an entire biomineralized structure. I think it's a calcified structure. And then the cilia actually pass through the pores of the calcified structure. So if you look on the left, this is work from Johan's lab, where you can see the tiny pores, and those pores are the only pores where cilia come out of. Just a really remarkable and a very strange, I don't think we understand the function in this context at all. Okay, let me switch actually, otherwise I'm gonna run out of time. Let me show this video of a diatom and a coccolithophore, and then let me jump to the marine snow data set. So to just really convince you that it's very important to observe these things in native environment, this is a data set we collected long time ago, and I think Gremmel's lab and a couple other labs in the same time also discovered this phenomena. Now, this is a diatom. It's a single, this is a centric diatom. Cosnodiscus is the common one that we have studied. And you're watching the same diatom change its density in 100 milliseconds. So you see it sinking. It has no flagella, no cilia. And this is literally cell density change as a function of 100 milliseconds. As far as I know, this is the fastest change in density. This is, I think, 3 to 5% change in density. And you can see every moment right there. There is no tether here. There is no interaction with the surface. It's just innate behavior from single cells. And that kind of changes your view of thinking about, the cells. And then the fact that it's so fast, I don't think it's settled per se in terms of why this is so fast. Another kind of a context is this was done in Puerto Rico. We went to the Arctic. We found the same behavior all across. Now these are freshly caught organisms out at sea. 20 minutes after the capture, the entire same blinking dynamics is actually true. To just push the limits of what we can do in terms of resolution, very recently, we've been working a lot on coccolithophores because they are very important. So this is data sets with Kay Beidel's lab. And we've been able to actually track not only individual coccolithophores, which are now 5 microns, but actually individual coccoliths themselves, which are even smaller and act as a ballast. So this is really pushes the technology to as far as it's currently true. So this is a 60x long working distance objective, and we can track these sets of organisms. And of course, the reason we're interested in this is aggregation assays and thinking a lot more about how marine snow is generated. Okay, so that's all I wanted to say about organisms. Let's switch to a very particular story around marine snow. So this is based on the expedition in the Gulf of Maine. Another technical thing that we had to build is on the left, because the ocean is quite rough. All the data sets that you will see is actually on this 2-axis gimbal. So the machines are mounted on this gimbal that allows us to stabilize it. And let's just watch through some of the data set. So the first thing we did is we mounted sediment traps. We bring the particles, and we essentially one at a time. So this is a very low resolution assay, slow. One at a time, we collect these sets of particles, and we measure their dynamics. And I'll let you kind of point out something quite strange that you see. So now you're watching a marine snow particle. And from each one of these data sets, we can calculate its sedimentation velocity. So on the left is, and I'll show high resolution data sets for these for a second. This is roughly around 100 or 120 particles. And you notice kind of a dispersity and the range from 0 meters per second to 200 meters, per day to 200 meters per day, sinking velocities. But the surprise sort of came, and of course, this has been intuitively known for a while, that, you don't really see a good trend. This is not a size-dependent thing. You would assume that density has some heterogeneity, but still this was in a bloom that was diatom dominant. But one of the things that we got interested in is really looking at much closer to the fluid structure interaction in the system. So I'm going to now show you a video up close for one of these particles. And of course, this is a very large data set now. At this point, we're around 1,000 particles. And let's just watch this up close. So of course, the fluid has been seeded with particles, and then I'm sure you all can see this massive added mass of this fluid that's actually traveling with this particle. And that doesn't make any sense if this was just a fluid. And we've been calling this now the invisible parameter, or comet-tails. And what this is essentially mucus. And what the mucus is doing is, so if you look at the flow field, you can see that zero velocity tail. And immediately it should occur to you that if you have this massive tail, the net drag of this object and the net density of this will actually be dramatically different. And this is quite scary from what I'm about to tell you in a second. So let's just watch that. Now we do this for every particle, around 1,000 particles that we have collected in 5 expeditions. And it turns out to be universally true that all of them have these massive mucus tails behind them. And in these massive mucus tails essentially can transition your sedimentation velocity that you would calculate from just, say, the radius of this particle. But now there is an invisible degree of freedom from 200 meters per day to 0 meters per day. So these are parachutes behind a particle. Some of you know kind of drag lines and spiders. It's this very similar physics per se. And one of the fascinating things about this is that often enough, the invisible volume associated with these individual particles that give us a sense of thinking about the overall volume in the mucus is actually double or triple sometimes the total size. And then a very important framework in this is, of course, we can label this. We can now label it in situ. We can measure this very directly. We do a lot of holotomography on these sets of particles, so we can actually see this and characterize it biochemically. But I'm going to spend a few minutes just sharing kind of the framework that this has led us to be thinking or rethinking about how we should be modeling marine snow particles, which is a two-phase system where there is a mucus, there is an effective viscosity associated with this, and it's a viscoelastic object, and it's sedimenting. And so these are the two sets of parameters. The one we will care about is the ellipticity A and B for the set of a particle. And we can write down essentially a sedimentation stress. And so when you think about this tail, and the average size of this tail is dependent on the viscoelastic relaxation of this material. And we now have methods and techniques, even in this in situ measurement, to actually estimate. So we show the estimates for that viscoelasticity. And the self-sedimentation stress term actually gives us how much will this tail stretch out. We can rescale much of this and essentially show a non-dimensional parameter that allows us to map all of this data into kind of a master curve associated with this, which gives us a proportional, depending on the amount of mucus you have, what would be the effective sedimentation velocity look like. And I think the way I'm plotting this here is kind of from a remineralization point of view, because what truly matters is what does this slowness do to the particle itself. And one of the key ideas is that the residence time essentially doubles for these particles in the first, say, 100 to 300 meters, which is very scary because that implies that most of the bacteria will have plenty time now to be able to actually work on this and remineralize some of this back in. And so this doubling of the residence time, I think now we are starting to write down sets of large-scale 1D Earth models to show what does that mean in the impedance of sequestration. How much, I mean, if we, whatever numbers that you end up using in terms of gigaton per year for sequestration, what would be the impedance and how much would it slow down because of this essentially residential? And very recently, an experiment that we did in kind of the California current, we're also starting to see that bacteria, when introduced in this, I mean, of course, this is in a native environment. We're doing all of these experiments with bacteria that are being present. The mucus volume, even from a point of view for a day, it doesn't change over time. And so effectively, you have these things slowing down as the progression of the degradation essentially begins in these sets of particles. And then the other thing that's on the archive paper now is you can see on the left is kind of the overall original data. On the right is the rescale data for now what we are calling a modified Stokes law for this. And there is still kind of one of the other things that we are currently measuring with an independent parameter is also the ballast and the density associated with these sets of particles. Because what's important is we want to remove the heterogeneity that might be present in a few sets of marine snow particles might have ballast and might have lots of diatom content while the other ones don't. But kind of the moral of the story of what all of this comes down to be is that there is a significant slowdown in sedimentation of our biological pump. And I want to say this a little more explicitly. This is a result that worries me a lot, just personally. You know, I think we are a lot dependent on the ocean and thankful to the ocean that it sequesters a massive amount of carbon. But unless we include biological parameters, you know, our estimates and how these sets of things would change as a function of time is actually really up in the air. And to a sense, where from some of the expeditions we've actually seen the particles we collected had absolutely no sedimentation. And again, you know, one of the things that's worrisome is as yet we don't know how that is dependent on the microbiome locally. We don't as yet know the sets of stress state. There is one assay that we are running currently on viral infections to show whether if there is infectivity in these cells, whether there is essentially a larger amount of stress, larger amount of these mucus physical tails that could be generated. And then kind of, so I just want to say that more explicitly is I am very happy that we went out there and measured this. I'm not so happy with the result of what it turned out to be significant on the opposite side of the direction. And just kind of my anxiety around the climate grows day by day. And the more we see, the more we have to be thinking a lot deeper about, and especially, I just want to emphasize the importance of microscale physics in all of these. And I think, you know, I'm preaching to the choir, but as a group, we need to communicate that to much larger scale modelers so that they appreciate and understand how dramatic some of these effects can be. So for some of you who might not have seen three-dimensional marine snow, this is what I meant by holotomography. We do a lot for that for one-to-one particle. So the data set that we are releasing has individual particles. It has the sedimentation and the flow rate. And just, we mentioned this in the paper, it's important to say this. We do not see any evidence of true porosity in these particles. By porosity, what I mean is effective flow. And this is what I was excited about when I started this project almost 6 years ago, that we're going to see flow through these particles. But it turns out the mucus plugs all the holes. And so we don't see this true, although it's porous from a structural perspective, it's porous from a mechanical perspective. It's a very soft object, but we don't actually see flow through like pores because the invisible portion that you might think that looks like pores are actually plugged by the mucus. Okay, I'll just show this one data set and I want to transition to then a discussion because I already see it's 8:50. This is a very new assay. It has worked very recently. I'm very proud of it. We can now do, during sedimentation, actually track single bacteria at sea on a sinking marine snow particle. So what you're watching is a single particle that has been labeled for the bacteria. So those little dots that you see, and then right there, what is passing in your field of view are bacteria that chose not to jump on this. So for the first time, I believe, we now also have assays and this is a big focus of the work right now, where we can watch the dynamics of who's coming on and who's coming off using, we have a confocal now coupled to the GM, and that's now will enable us to be able to really do three-dimensional tracking for these, including the single bacteria, because that's an important aspect of the change that occurs. We can also directly now at this point measure the polysaccharides being made. I don't have that data here, but I think that's, and I have run out of time. I was going to tell you guys something about aggregation, but I think it's much more fun to do discussions. So let me just mention the work that I just mentioned around marine snow was done with a very talented postdocs, Rahul Chajwa, who's actually also in the job market. So just in case, if you guys are looking for talented people. And then Ellie Flum supported some of the imaging side and collaboration on some of the expeditions with one of the NSF GCRs we have with Ben and Kay at Rutgers and Hui. I will stop here. There's a lot of other things that I would have loved to shown, but I never keep track of time. I'll leave this fun picture in the background for what happens when you plan to do field experiments and unwelcome guests show up. This was an unwelcome guest in the, I'm very happy to see this entity, but it's kind of scary as well. So we had to abandon our experimental site for some time. Okay, I'll stop there. We can turn this into discussions. I'm very happy. I'll unshare my screen itself so I have a chance to see you all.
Thank you very much, Manu. I think we are very close to the hour. It's 3 minutes to the hour. Maybe we have time for 1 or 2 questions for Manu, because we really want to keep it on the hour.
And then I'm happy to stay a little longer if the Zoom is open. You can stop recording. Just
okay.
I think, yeah. Anyway.
Yes, I kept a little bit more time for the Zoom in case. Okay. Questions from the audience, if there are questions.
Yeah, I see Jules' hand. I saw
Sure.
a couple of hands.
Yeah, Jules, go ahead.
Yeah, hi, greetings from Cape Cod. Can you guys hear me? I just want to make sure. Yeah, so fabulous talk. You have a global perspective that I admire and a level of energy that also I admire. Just as we've been actually developing an underwater robot to track marine snow in situ. And as far as I know, there's only one other group that's ever done that. And we would be delighted to share that data with you. As far as I know, talking with the microbial ecologists as well as the marine snow people, the exopolymers are really hard to image. Mm-hmm. And I'm wondering if your holo microscope can do that. So with much appreciation and with due respect to the time, I enjoyed very much your talk. So nice.
Thanks, Jules. I mean, I would love to chat. I think one of the big things about these open data sets is really about multimodal data sets that we can release. So I think I'll catch up with you. I'm very intrigued by the in situ set as, and then we can also, we can talk offline on the many of these other phase contrast techniques as well.
Yeah, well, we'll be doing our first trials in the next few months. So I'm not bragging about history.
That's
I'm talking
awesome.
about the future. Sorry.
Yes. I see Jonas's hand. Good to see you, Jonas.
Yeah, good to see you, Manu. Thank you very much for your talk. Very nice. I have a just a quick question. How does the sinking law that you propose, how does it compare to like the early days measurements of sinking rates as a function of size from like 1980s?
Yeah, I mean, I think it's
different.
It's a function of, if you look at the kind of rates of the differences that I showed from 0 meters per day to 200 meters per day, that's kind of the total. And when we do, one of the challenge in our data set, and if you look in the supplementary of the paper, we actually, on request of reviewers, which I very much appreciate, we actually put our data set in Kale's 2019 paper, which was a collection of 30 different data sets. And we put our entire data set right on top. And you can see that it's significantly slower. For majority of the particles, it can often be even an order of magnitude slower. because it's a function of the mucus and the amount of mucus associated with these particles. To a point where, I mean, some of them are not sinking, and I'm not saying that that rate, it really is a function of time. The number of these mucus tails being released is a biological parameter. It's a function of different stress parameters that we've been thinking about. And then there is also, we report in this study, there is natural fracture itself that we also see that also changes. So you can have a slow sinking particle, it fractures and gives rise. I think the theory is very similar to be thinking about what happens, say, rain droplet, that you have these critical sizes emerge. Right now, all our data set is recording around, shorter time scales. So this is really about instantaneous sedimentation, but we really have to be thinking about evolution of sedimentation itself as well. But we compare that with the old data set, the number off the top of my head I can remember is for the largest mucus size, it's an order of magnitude slower. And for, the estimates around, if you really have no mucus, then there is no problem. I think then we have a good way of measuring density. The problem is from photographs, you cannot infer and predict the density of these. And so that has changed. This is why we do a lot of holotomography on this, that we back calculate the ballast using other techniques. So at the least, the heaviest component, which is the mineralized component, we calculate from other methods so that we can also incorporate that in our data sets.
Maybe we can take a question from the chat as well. So Orkun Sawyer, if I'm saying it right. So hi, Manu, quick question. Have you explored freshwater environment with the GM?
Yeah, I think we take these machines everywhere and we study several freshwater protists. The entire story started with freshwater because of schistosomiasis. So there is a couple of pathogens that we've been looking at itself in the aquatic ecosystem. And then the thread around the, I think I have never worked on lakes, but I know there are a couple of expeditions and people that have been starting to look at lakes in the Alps. And so if you have a good suggestion of an interesting kind of deep ecosystem that's understudied, I would be super excited. I think much of the time, we focus on aquatic species. I have not as yet focused on the ecology of some of these aquatic reservoirs, for example, other than we have talked to a few people in the Alps.
Okay, love to follow up on that at some point. Thanks.
Would love to, Orkun. Yes.
And
I have a quick question. Hello. Thanks a lot for this cool talk. I'm just wondering whether you can relate the change in sinking velocity and behavior to the sedimentation rate. So you had the sediment traps. How do you bring this together?
Yeah, so I think kind of one of the challenge with when we do the sediment trap, we do the bulk set of measurements of how much we captured per unit time. And then we have the direct capture of what the object sedimentation rate looks like. Now, the problem is that the moment you put the sediment trap, you don't know whether the particle that you captured was right above it and it just landed, or it came after a day of a journey. And so I think kind of one of the big things that we have been building is building larger and larger data sets for a direct measurement and so I think, in some sense, this is such a critical change in how these particles sediment. So I'm not trying to per se, one thing that we have done is we have tried to put our data in the old data sets, but I am not a big fan of fitting parameters and like an infinite number of fitting parameters. And I'm actually critical a little bit in the papers on that approach, because although it helps us incorporate the global context very quickly, but at the same time, it hides behind some of these microbial perspectives. So I am in conflict a little bit with my own self. I would like to be able to kind of backdate all of this and say, oh, there is something magical we have found that we could correct for in the past measurements. While on the other hand, I am of a proponent that we really need to increase high fidelity measurements. I mean, UVP is one we have been looking very carefully at the UVP data, because at least I know where the depth is and I know the shape per se. But we cannot infer anything like this from those data sets. We tried it, and it kind of, that was hard. And so
Yeah,
right
just
now,
a quick follow-up. So how if you would calculate your sedimentation rate from your imaging, would that still fit with your sedimentation traps? Because you have done it basically. So I think you could try to link it, right?
Yeah, no, that we can link. You know, for our data sets, we can link that and we can show the amount per se. And we've shown, so sort of in these measurements, we are doing the total flux that we are collecting for all our traps. I think these are only data sets for the 80 and the 150 meter trap, but we have a lot more data from the recent expedition where we can also try to see whether this corroborates with the Martin's curve. We have now 3 depths. So for our data sets, we can do something like that, but we have a very direct measure of the actual rate.
So
thanks a lot. Yep, cool.
I'll take a question from Auria and maybe Jonas, and then a question from the chat. And I think we should stop soon because the meeting will end at 12:15.
And I'm sorry, I have a tendency to rant away. I wish I could be more focused, but
it was exciting, no problem. Auria?
So thank you very much. As usual, yeah, I won't say a lot. It just was wonderful because so the question is goes like that. So the particles, as they sink, they evolve. Yeah, they fragmented. They collect more materials. And so, but I think the system you showed us does not replace the water. Am I correct? Or this is something that?
Yeah. So there's two kind of a context to it. There is the long-term tracking and the short-term tracking. So the first batch of data sets that we have collected are really about the instantaneous life of the particle. And then there is a second data set that we are collecting, which is separate, which really is about the long-term life, where even on an expedition, we will stay with one particle for a whole day. Now, our challenge is that it's quite costly to be at sea. And so we have to kind of balance between, should we just collect a whole bunch of data or should we just focus on? So we try to do both at this point. And then this in other system, we have mechanisms to essentially replace the water column. And we can also replace it with the water at the depth that is coming from the same depth with the CTD. We actually, so the microbial content we can actually change. It's a more complex wheel. We have ways to actually block the wheel, replace a segment. So it's a halfway block. And then we use block wheels all the time as well for when we are looking for short time scale tracks, because the accelerations of the boat can couple in. So we have that, but I didn't show any of that data. I didn't show any bacterial data other than just that one quick video.
Okay, Jonas, maybe?
I would
just very quickly
comment. I would like to speak with you about it. I have some basically data that I collected that look at the very long time, several days, but replacing all the time the water, and maybe we find some similar stuff.
No, I mean, that would be fabulous. And I do agree with you that that context is changing, that this object is actually traveling through many ecosystems. Yeah.
Just very briefly, you mentioned data from deep waters. Do you see a lot of big particles down there?
I would say more dense particles. We've only looked at these data sets, so we haven't physically put our own traps per se below. I think the deepest one we have put is like 600 meters this year. We have not put anything below that as yet. And, I am generalizing a little bit about the particles that we see. I mean, this is large number of these 6 expeditions were in completely different waters. It really is a function of what's going on top. So there are versions where it's been a coccolithophore bloom. Sometimes it's been so diatom dominated. So to answer that question, one of the key things to sort of kind of anchor it in one particular part of the ocean. And we now are looking at the BATS data set in Bermuda, where I do believe they have a very deep trap. So we are just getting started, but it's all going to depend on the function of what's in the top water as well. So I think this is kind of the tension between the desire is to generalize, but the ocean is so heterogeneous that we have to really be thinking about them as sections. I mean, I'll give you one idea, which I was quite shocked with. For 600-meter trap that we did in the California current this summer for a month, we could see 600 meters below single diatoms and abundant. So forget about the particle. They were making it there in abundance all the way down. And I just wasn't expecting that. And these are very large diatoms, massive chains, but with no association with anybody else. And that surprised me. Is like, I was like, oh, of course, we're going to only see these sets of things. And I would say maybe 25% of the biomass was in these single diatoms, which is kind of, I mean, I don't have a good explanation for it. There's no light there. So, and I think we believe there was a viral infection. There was something going on that like, the diatom just give up. And of course, they make it to the ooze. The diatom ooze is basically, a lot of that is also single cells. So I think my challenge, just kind of as a comment, is really around this idea that it is also hard to generalize if we don't have a good framework of the ecology on the top too.
Manu, thank you very much. I think we still have maybe 1 minute. There is a little question here, and I think we should stop. It's from Arthur, I think. Are you able to tune the pressure inside the GM, mimicking depths while sedimenting?
Yes, I really wanted to show you guys some pressure data. That's Adam in the lab has recently been able to, we could do constant pressure, but now we can do programmable pressure. And I'm looking for the photo. It's going to take me too long to find it. But we can go down to 40 atmosphere at this point. And I wanted to show a photo of what happens when we go to 41 atmosphere. And, you know, you can imagine the wheels explode basically. So it's I don't have that picture, but yes, I think the answer is 400 meters is kind of our upper limit right now. I don't think that's it's just a technical issue. We are working with a couple of glass companies right now to improve that. But, and of course, the whole point of this is we are running assays to see what, you know, how and when these things detect pressure.
Thank you very much, Manu. I don't want to be abruptly cut. So thank you very much again. And thank you everyone for attending. I hope to see you for the next one. Thank you very much. Bye.
Bye, everyone.
Bye.